What if there was an acorn way up in the tree? What if there was an acorn way up in the tree?
What if there was an acorn way up in the tree?
If the acorn fell, is it possible to know the speed as it hits the floor? Do you need to know the mass? The equation you need to use is gravitational potential energy, gravitational potential energy, which is mass times by gravity times by height.
Which is mass times by gravity times by height.
So that involves mass. There's another equation to work out the speed that it hits the floor, and that is kinetic energy is a half mv squared. Kinetic energy
is a half mv squared.
M again stands for mass. M again stands for mass. So kinetic energy involves mass. Gravitational potential energy involves mass. Strange thing is that the mass will actually cancel out. So you don't need to know the mass to find out how fast something is travelling when it hits the floor. I'll show you when I get back to the lab. So say for example, I drop this ball from 1 metre, because I'm also going to work out how fast the ball is going when it hits the floor. But if I drop this ball from 2 metres, or if I drop it from 3 metres or 4 metres,
what if I drop the ball from the top of the tree?
You're gonna drop it, Billy. We'll go. To work out gravitational potential energy, if an object has a mass and it's a certain height above the ground, it will have gravitational potential energy because gravity has the potential to pull it back down to Earth, and it would release energy as it does that. To work out gravitational potential energy, you take the mass of the object times by the gravitational strength on the planet that you're on and multiply it by the height. So we say gravitational potential energy is mgh. Mass times by gravity times by height. Make sure you convert your mass into kilograms and make sure that your height is in meters. Gravity on Earth is 10 newtons for every kilogram of mass that you've got, and by using those units, that'll make sure that the gravitational potential energy comes out in joules. All energy is measured in joules. Kinetic energy just means movement energy. If something's moving, it has kinetic energy. The equation for calculating the kinetic energy is a half mv squared. That's a half times by mass times by the velocity squared. Remember to take the velocity and square that first, then multiply it by mass and then half it. So for any object that's fallen, as the object falls, the gravitational potential energy it had at the start gets transferred into kinetic energy. That'll show you what I mean. Take a diver. The energy at the start, since the height is the maximum, then the gravitational potential energy will be at its maximum. Once it starts to fall, the height will decrease. So the gravitational potential energy will always be decreasing throughout the fall. Now at the start, there's no kinetic energy because the object's not moving. So at the start, the gravitational potential energy is maximum and its kinetic energy is minimum. Halfway down, because the height is only half what it was, that means that the gravitational potential energy will only be half. The law of conservation of energy says that the energy at the start has to equal the energy at the end. So if you've lost half of your energy, it must have turned into a different form of energy. Now if we assume that there's no energy loss, then the energy that's been lost by gravitational potential energy must have been gained by kinetic energy. And at the end, because the height is zero, if the person is splashed into water or if they've hit the surface, the gravitational potential energy will be zero because the height's zero. Where's all the energy gone? Well, it's all turned into kinetic energy. So the kinetic energy will be at the maximum. So what we can say is the gravitational potential energy at the start will equal the kinetic energy at the end. But that is assuming that the law of conservation of energy is correct. and that no energy has been lost. In real life, energy will always be lost as heat from a system. It gets wasted, and that's because of friction. The heat goes into the surrounding environment, and it's not available for any further useful energy transfers. Let's consider the energy transfers that take place when a skier skis down a mountain and when an avalanche follows him.
Oh yeah, oh yeah, dude. Holy Yesterday, Abbey conditions were a little spicy. As soon as I started skiing, like first turn, everything ripped out on me, and I ended up just kind of having to look for the island of safety. At that point, it was just like, take all the speed you can and just try and get out of this thing. Avalanche, avalanche, avalanche.
The gravitational potential energy of the snow at the top of the mountain turns into kinetic energy as it falls down the mountain. The further it falls, the more kinetic energy it gets, so it speeds up. The skier's gravitational potential energy at the top also turns into kinetic energy as he falls, so hopefully he gains more speed than the snow, so he can outrun the snow. Let's consider the energy transfers when a pendulum swings. This is often a question in an exam. It'll ask you about a person on a swing being pushed, and they'll ask you to consider the energy transfers.
If I release it from this height and it swings, then when it reaches here it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher. 2, 1, 0.
The pendulum starts with maximum gravitational potential energy because it's at its maximum height at the start, and zero kinetic energy at the start because it's not moving. As the pendulum swings, it gets lower to the floor. Since its height is decreased, its gravitational potential energy will decrease. Where has the energy gone? It's turned into a different form of energy, in this case, kinetic energy. This is called the conservation of energy. The energy at the start has to equal the energy at the end. However, because of air resistance, some energy is lost as it swings because the ball needs to do some work pushing the air molecules out of the way. This causes the ball to not get the same height that it started at when it swings back to the man. That's why it doesn't break his jaw. Energy that gets wasted as heat in a system like this is no longer useful energy because you can't use that heat in further energy transfers. If two surfaces are not rubbing together, you can still get friction caused by air resistance. We call this drag. See my video on drag.
Physics works and I'm still alive. See you Wednesday. 2, 1, 0.